Hey guys, we're back. We're going to take a look today, right now, at reverse it again, but we're going to move on and we're going to look at numbers 3 and 4. So we did numbers 1 and 2 together in the last part. If you have any more questions about that, go back and look at it again. And please, I cannot stress to you enough, every piece of information that I'm getting from this is all coming from this table right here, which is on your sheet titled The Relationship Between a Function and its First and Second Derivatives. I am getting 100% of the information on how to sketch the graphs of the original function from its derivative using this table. Okay, so refer to it back and forth to find where is the function increasing, where is it decreasing, where is there a local max or min, where is the function concave up, where is the function concave down? Where does the function have a point of inflection? And notice we're not finding the second derivative this time. That's true when we have an equation, but when we have a graph, all we need to do is analyze the graph of the first derivative to find all this information. Okay, so let's go back. I'd actually like you to try numbers 3 and 4 on your own. So I'm going to ask you to pause this video for a minute and to actually try 3 and 4, and then we're going to take a look at the answers and I'm going to explain them to you. And then think about for just a second what it would mean if you have a constant piece in a function versus a linear piece. And what would the original function look like if its derivative was constant versus if its derivative was linear or curved? Either way, okay? So I'd like you to actually try number 3. You can also try number 4. There's only one thing here that makes this different when you try it, and that's that you're given an initial condition. You're told that the f of 0 is 0. So that just means that when you come over to sketch the graph of f of x, you put a point at 0, 0, and that just needs to be a point that you go through. Doesn't mean it's a max or a min or anything like that. It's just a point you need to travel through. On number 4, it says the f of 0 is 2. So you plot that point, and then that allows you to have more of like a vertical understanding versus where you're sketching multiple examples. All of these are correct plus infinite more. All of these are correct plus infinite more. These you won't have perfectly because you still don't know how high to make a max or how low to make a min, but it still allows you to have a better feel for where to start your graph. Okay, so pause this video right now. In your packets, try numbers 3 and 4, and then come back and take a look at the answers in a moment. Okay, now that you've unpaused, take a look at the graphs that you have drawn and the answers, and let's talk about them and make sure that you understand. Here's the graph of the derivative. Notice that this derivative is positive from negative infinity to about negative or 0.75, on the x-axis. And then again from around like 3.75 to infinity. So that is where f of x will be increasing. The derivative is negative between about 0.75 and about 3.75. So that's where f of x will be decreasing on that interval. Because we have a sign change from a positive derivative to a negative derivative value around x equals 0.75, that would make it a local max. And because the derivative changes from a negative value to a positive value around 3.75, that means it will be a local min. Okay. Notice that the derivative is decreasing from negative infinity to about 1, and also from 5 to 6. So that's where the original function will be concave down. And the derivative is increasing from 3 to 5 and from 6 to infinity. So that's where the function will be concave up. F of x, the function itself, is going to be linear versus it's going to be more of a quadratic or curve shape on the other parts, but it's going to be linear from 1 to 3, and it's going to be going downhill with a slope of -1 since that's its constant function value between 3 and 5. Concavity changes at x equals 5 and x equals 6 because those are where there's a local max or min in the derivative. So now if we go and sketch it again, we sketch the point at 0, 0. According to the notes that we took, if you even need to take them. Some people don't. You're going to start off increasing concave down, hit a local max somewhere around x equals 0.75. Then you're going to be concave down and decreasing until x equals 1. This is where we have a linear value and a slope of -1. And mine's not even a great slope of -1, but something like that, until about 3. Then we switch to still decreasing concave up. So it kind of looks like this right there. Local max at about 3.75. Now we switch to according to the notes, concave up increasing until right around in there. And then we switch to, well, actually more like right there with 5, we switch to concave down. And then at 6, another point of inflection, still increasing, but concave up. Now, yours should have that general shape. It should have a local max right there, a local min right here. All concavity and intervals of increase, decrease have to be the same. But you may have drawn it like this. Okay, your max might have been there. And then you may have done something like this. And, you know, that's okay. As long as it's got that shape and all the concavity and stuff's correct, it might not have the exact Y values. Okay, let's take a look at number 4. So on number 4, the derivative is positive between 1 and 6.5, and then from 8 to infinity. So that's where f of x will be increasing. The derivative is negative from -infinity to 1, and from 6.5 to 8.5. So that's where the function will be decreasing. Because we change from negative to positive at x equals 1, that means there would be a local min. And also that same thing happens from right there from negative to positive. So around 8.5 we'll have a local min. Around 6.5 we change from positive to negative. So that's going to be a local max. The derivative function is increasing from -infinity to 2 and then from 8 to infinity. So that's where the original function will be concave up. And the derivative is decreasing from 5 to 7, so that's where the original function will be concave down. This constant piece right here from 2 to 5 is going to be a linear segment, because the derivative of a linear segment is a constant segment, with a slope of 3, which I didn't do a great job of making it look like 3 right there because it was really steep. But if you were asked, that's what its actual slope would be. And there actually are no points of inflection, because you switch from concave up to linear right here, and then you switch to concave down from linear. And then this section is also going to be a linear piece. So there's no max. Notice there's no local max or min in the derivative function, which is why there are no points of inflection in the original function. It's more like it's just switching from linear in there, and so it doesn't have that happen. Okay, so follow the information you took. We have to start off, remember we have to go through the point 0, 2. We start off decreasing and concave up till we hit this local min at x equals 1. Now, according to the info we took, we increase concave up till we hit 2. We technically have a linear segment with a slope of 3 from 2 to 5, even though, as I mentioned, mine should be much steeper, but I ran out of space. At 5, we're increasing concave down until we hit the local max around 6.5, decreasing concave down until we hit this linear segment from 6 to 7. It has a slope of -1. I did a much better job with that slope. Now we decrease concave up, hit a local min at 8.5, and then increase concave up the rest of the way. Yours does not have to be exactly the same in terms of those Y values, but it has to have the same shape, same places where its concavity is the same, and same max and min, and increase, decrease. Okay, let's try a few more. I just want you to try some extra practice. Same thing again. The graph on the left is going to be the derivative, and the graph on the right is going to be where you sketch the original function. I've left you space. If you want to take notes, please feel free to do so. for numbers 1 and 2. And then when you're done, I'm not going to show it to you, but down here is the key. I'll slide up in a minute and you'll be able to look and see if you have them right, and look and see what kind of issues you're having and that kind of thing. And when we have class again, I will definitely be doing much more with this. This is just the beginning of it, but I wanted you to have a good feel for this because we're going to be doing a lot of these in the next couple weeks, and you really need to have a good idea of what's happening and where you're going. Okay, so I'm going to ask you to pause it now, do numbers 1 and 2, and then come back and I'm going to scroll up for the key and you can check 1 and 2. And then, like I said, when we have class again, we'll go back through it. Okay, take a look at your answers. If you have any questions, of course, you can ask in recitation if you have it, but also please ask in class. We will be doing the rest of Reverse It. Notice we did not do numbers 5, 6, 7, and 8. So we will be doing those in class next class. And then we'll also be doing the rest of this handout, sketching the graph of a function from its derivative. So by the time we finish next class, you should be pretty good with this. Right now, it's not easy for a lot of people. For some people, they can literally just look at the graph and instantly just start sketching the original function. I am not one of those people. These notes are really helpful to me and I go back and look at them. But whichever way it is, you will get better at it. I promise. It just takes some time to get used to it. Okay, see you in class.